Hi, everyone. Glad to participate in MICNON 2021. This talk is on Koopman operator, geometry, and learning of dynamical systems. The approach to learning of dynamical systems I'll present here is based on the concept of representation. And the key to it is understanding of invariant subspaces of the Koopman operator, the operator that's been classically used to study measure preserving systems. And today, as we do a lot of work in dissipative systems, it's in mathematics known as composition operator in general. Kind of a mission statement to Koopman operator theory is that spectral objects associated with a class of linear representations help unravel the state space geometry and enable model reduction and control. All of this for high dimensional systems and enables data-driven analysis as well. And I'll show or give some insight into numerical methods for linear representations of dynamical systems, even nonlinear dynamical systems. But I'll also present a new concept that I called an eigenmap, where the idea of embedding a nonlinear dynamical system into an infinite dimensional space and then looking for linear representations is kind of inverted, saying we have an operator, can we find nonlinear finite dimensional representations for a class of observables or class of functions for that operator? And my thoughts here are mostly from the August 2021 issue of the American Mathematical Society notices, and the link is there right here. So let's start with some definitions. We have a set of observables on phase space M. We'll denote observables by F. This phase space or state space denoted by M. And then observables to start right away are going to be into the complex plane. Eigenfunctions of the Koopman operator can be complex. So it makes sense to start working with complex observables from the beginning. The Koopman operator is the composition operator. For an observable F, it's a composition of F with the map T, where T is a mapping from state space M to M, or in continuous time case, if we have a flow of a vector field denoted by ST, then UTF is F of ST, where X labels a point in M. And that's true for every T element of R. So here we have if the system is invertible, actually we end up having a group of operators UT instead of a single operator. The references, original reference to that are Bernard Koopman in 1931. Karleman also had a paper in 1931, a little bit after Koopman, and then Koopman and von Neumann followed closely with another interesting paper on statistical properties of dynamical systems in 1932. This point of view was not used. Was used relatively sparsely. But then in the last 20 or 30 years, with understanding that analysis and formulation of spectral objects like eigenfunctions can be done from data has gained some momentum. This is perhaps a complex a concept to start with, but it does represent in one formula kind of the gist of what the approach Koopman operator theory is trying to do. Here G is the set of observables, Z is some label for that set of observables. For example, in a fluid flow, Z could be a spatial point, three-dimensional, so Z1, Z2, Z3. X is the point in state space. And so it turns out, as shown in this paper down here, that under some technical assumptions, we can split the action of the operator into this UTS, so an operator that we call UTS, and then UTR. Classically, these terms stood for singular and regular. And this part here can be further decomposed into G star. This turns out to be the time average at, let's say, for a fluid flow spatial point Z, the time average of the observables you're taking. That could be pressure, temperature, velocities, whatnot. And then a regular part where lambda j's are some coefficients here. They turn out to be eigenvalues of the operator itself that drive the time evolution. And then phi j's are the eigenfunctions that satisfy in discrete time u phi is lambda phi, and then continuous time ut phi is e to the lambda t phi. And then this projection here of G onto eigenfunctions, and we'll deal with this later because that's a very high dimensional projection with respect to some possibly a very high dimensional projection, a projection in a very high dimensional space. And in this part here that represents the effect of the fact that the operator itself can have continuous spectrum. Further refining, we could denote this as SJZ, and today we call these things Koopman modes. I call them shape modes originally. Phi j's are the Koopman eigenfunctions. This is the time evolution, which is exponential. Lambda j can be complex, so this potentially could be oscillations or growth or decay or combinations of those. This is the time average, and this is the continuous spectrum part. And what you'll see in the talk today is that this part here, if it's the only thing we have, so we don't have the continuous spectrum, then one can find a finite dimensional linear representation of such a nonlinear system that has this expansion. And if we don't have that part, except possibly for time average, and we have continuous spectrum, then the operator itself can still have a nonlinear representation that is finite dimensional. So whether an operator has a finite dimensional linear or nonlinear representation in some sense depends on the properties of its spectrum, and that is the main message of this talk, that there is a precise way in which one can determine whether a linear representation of a system is possible or whether a nonlinear representation of system is perhaps possible, but certainly necessary, and that's in the case where we have continuous spectrum. All right, the way we approach the problem of realizing, or rather embedding the nonlinear system into an infinite dimensional space is understood as follows. Let's have this set here be an abstract set with an abstract point P in it. X is going to denote the states. So this is a system of observables that we denote states. And then P prime is the point that by dynamics, P is moved into. Now, associated with that P prime is X prime. So remember, X is a vector set of observables. We have n of them. And so another way of representing that set of observables is choosing a basis on this space of functions fj that span a space. That if we have a measure, that could be a Hilbert space of observables, so L2. But in that case, X, they have some coefficients Cj that when we sum over the basis functions represent the state functions F. And of course, then the point P is represented by these coefficients Cj here, up here. And now the composition operator itself, it's its own action on an individual function fj can be represented, again, under some technical conditions, as a matrix, infinite dimensional matrix djk, multiplying fk's. Putting these two together, so acting with u on x, we get that x prime is this double sum over djk acting on individual fk's, of course, multiplied by coefficient cj, and that represents the original point p prime, that abstract point that we started with. So there's clearly a way of going from an arbitrary nonlinear dynamics to a linear dynamics that's represented by an infinite dimensional matrix, and all the way back to nonlinear. So all the information is contained in this linear operator. And as I said, I'm going to ask the question, when can this be replaced by a finite linear action, or actually a finite nonlinear action? So that's kind of the key question in this talk. Much more on the background numerical analysis applications is a plug for the book, is in this book, the Koopman Operator in Systems and Control, that Alex Mauro and Yoshi Suzuki and myself edited. So the outcomes of the previous type of formula is that the Koopman eigenfunctions that feature in it, they represent the geometry, in particular the level sets of these eigenfunctions give you the geometry in state space. The projections of sets of observables on Koopman eigenfunctions give Koopman modes. These are equivalents of eigenvectors in linear systems. And if we learn eigenfunctions and we have no continuous spectrum, and modes provides us with a model. And in fact, that would be a linear model if continuous spectrum is not there. And this can be done entirely from data. So these are the key kind of messages of the operator theory approach. Let's now go to the technical part of representation theory for dynamical systems. So I'm going to start with a set of all complex functions on M, and as the space of observables, it's clearly a linear vector space over the field of complex numbers. And if we define a discrete dynamical system on it, and let little m be a point in state space, then the iteration of the map is just m prime is labeled as Tm. But any such map defines this composition operator that I have talked about in the intro. And so here is the definition for representation. If we can find a finite set of functions labeled by f, boldface f, and capital F is a map such that the action of u, the operator on f, is exactly the same as applying a possibly nonlinear map, capital F, on the set of functions f, evaluated at the same point. So this set of functions, set of observables f, and the map, capital F, that is the representation. If that's a real set of functions, then the representation is real. And here is a simple example. Let's have a two-dimensional torus. And let's say that the mapping is abstractly given by just taking a point on the torus, translating it in one direction by angle omega-1. And so that's around the symmetry axis. And in the other direction, so along the cross-sectional circle with angle omega-2. Now, if we choose f to be z1 and z2, where z1 and z2 are both points in the complex plane, so z1 is point on the complex plane on, let's say, a unit circle, then the capital F is just obtained by multiplying z1 with e to the I omega-1 and z2 by e to the I omega-2. This clearly just rotates things around one direction, and the other direction. And so this set of functions, z1 and z2, on the torus, which is our state space, and the mapping that I have defined here is actually a linear complex representation of the mapping T. So sometimes very efficient representations, linear representations can be immediately obtained if you look at complex observables rather than real observables. Now, some more definitions. This a representation can be faithful. It's called faithful provided the set of observables is injective. So if you have M and N be two different points, then F of M and F of N are different, or if they are the same, if M and N are the same, then F and obviously the evaluation of F of M and N have to be the same. So the representation is called faithful provided this mapping here with observables is injective. We can immediately restate the Takens theorem in terms of this concept. If M is a compact Riemannian manifold of dimension little m, and we need R level smoothness, so T is a CR map, and F is a CR function. In this case, it's real. And Takens proves that for generic F and T, the map F tilde given by this time embedding of size 2m plus 1 is in fact an injection, and so in fact it's an embedding. And so for generic F and T, F tilde and this capital F is a faithful real representation of T. So the capital F is really the mapping that takes the time delay set one step forward. So the Takens theorem can be stated simply in terms of this concept of representation. An n-dimensional faithful representation is efficient provided there is no function h, complex function h, and some j between 1 and n such that the jth observable in our representation is obtained as a function of the other ones, right? Because that would be clearly quote unquote inefficient. The reason being that the information in the other observables that we have already covers the grounds. And so the nice thing about representations, they play nicely with the key concept in Koopman operator theory, a key concept in dynamical systems in general, and that's the concept of conjugacy. So if we have two different faithful n-dimensional representations, then there is a bijection H such that that H is a conjugacy of representations. So if you start from G, apply H, and then the map F that represents that is the representation map, then starting from the same G and the other representation map, capital G, applying H, you get exactly the same result. So now, sometimes the representations might not be faithful, but still might be useful. And so a representation is called reduced, provided it is not faithful. We might have a 10 million dimensional system that we do not necessarily want to understand in the detail that consists of all the small scale variations and oscillations, but there might be some specific observables that are closed in the sense that if I know the value of that observable, I'll know the value of that observable for all times forward. And that would be a reduced representation. It would not be faithful, so I couldn't completely recover the dynamics of the full system, but it would still be useful. There is a precedent to this, of course, in ergodic theory and dynamical systems. If you have a measure mu and you have a reduced representation of some mapping T on the state space, where the components of this F are measurable functions, then the dynamical system induced on the representation functions, which is f prime is capital F of f, on the image of M under the observables, we can define on it the measure nu that assigns to any set A the value of mu that is assigned to the set F inverse of A. So if you take the set A in the embedding, and then you take the inverse of that set, that's a set on M, and then mu has that value. So mu is a pullback of nu, or nu is a push forward of nu, and that would be called a factor of T in ergodic theory. In the context of ergodic theory, F is required to be measurable, while in topological dynamics, the representation is actually required to be continuous. So if F is a continuous proper surjection, so there are 2 points in M that map to a single point F of M, and we have a non-faithful representation, then F, the mapping F, capital F, is semi-conjugate to the dynamical system T. So these classical concepts play well with the concept of the representation and the reduced representation in particular. In the case when we have continuous time T, and then we have a group of transformations, I call them here T, capital T, satisfying the group property here. TT plus SM is TT, TSM, and any such evolution defines an operator group under invertibility condition on T. And then the representation consists of a set of real complex functions and a group FT that satisfy that evaluating the observable at time T, starting from an initial condition M, is exactly the same as applying the nonlinear mapping FT to the set of observables F in the representation starting from M. So for fixed tau, U tau is a linear composition operator associated with T tau. So each tau, each fixed time, provides us with a single composition operator. And then we have a group of them provided we have invertibility of the original dynamics. So we can go a little bit further and say, well, the classical set of dynamical systems that is under vast use is ordinary differential equations. And so one can obtain the ordinary differential representations, provided that the limit when T goes to 0 of the operator action on the set of observables that one has divided by T converges and gives us what we can call a vector field V of M. And in that case, we obtain a finite set of ordinary differential equations. F dot is V of F. What is interesting about this is that that even for a geometrical set that is as complicated as the Lorentz attractor, which is a fractal, so the attractor itself being a fractal object, one can actually define a vector field associated with that object. So there is no requirement on the smoothness of the object, which is what we usually start with when we define vector fields in tangent spaces of sections of the tangent bundle of a manifold. So this allows us to through the operator theoretic approach to define differential evolution on objects that can possibly have complex geometry. So now the notion of representation and the geometry of dynamical systems are connected, and that connection is done by using the notion of a partition. So if we have a set M, then a collection of disjoint sets A alpha, where alpha is some index set is an element of an index set in C, forms a partition, provided that the union of all these sets gives the full set M. If we have an observable F, then we get a partition. How? Well, we take the level sets of F, so all the sets on which F, all the sets such that for each individual set, if you choose elements of that set, F of M is alpha. So a level set is just a set in which the function itself is constant. And clearly, that set of sets satisfies this condition, so it's a partition. And another important concept is that if we have two different partitions, then if we form an intersection, set of intersections of sets in each individual partition, we get another partition. And then we can define the finest partition, which is the partition into individual elements of the set M. So it is a little proposition that says that a representation is faithful if and only if the partition zeta F here is the finest partition pi. That should be intuitive. The reason being that pi is the partition in the individual elements. This just means that the intersection of level sets of these functions F are single points. Just imagine a two-dimensional space, Euclidean space, and your observables might be X and Y. And the intersection of level sets of X and Y is a single point. And so that's kind of an example of what this proposition says. So now a finite dimensional representation is a set of function and mapping capital F such that UF is capital F of F, and this capital F is n-dimensional. So that's the dimensional representation. So it's finite. Again, if the set of observables maps to Rn is real, and then we call the representation real as well. Also, we're going to call this representation linear if capital F is a linear mapping. And a beautiful example of this is if we find a single function F, we call it phi here, such that U phi is lambda phi. So this clearly satisfies this requirement, with capital F being just a multiplication by a constant and therefore a linear mapping. We can extend this and say, hey, how about we find a set of observables F such that UF is AF, where A is an n-dimensional m-dimensional matrix in this case. And in this case, we could call A an eigenmatrix of U, and this would again give us a finite dimensional representation. And similarly for the continuous time case, UTF, in order for it to possess a finite dimensional linear representation, should be e to the AT capital F, right? So in discrete time case, we have action of the matrix. In the continuous time case, we have the action of the exponential of the matrix multiplied by t. This should remind you of the time evolution in linear systems, and indeed, this side is, but the left side is really evolution under an infinite dimensional operator, the Koopman operator, the composition operator. Now, in the differentiable case, we get dUTF dt is AF, and if we assume that A has distinct eigenvalues, and we define the complex inner product by this convention here, then the eigenvalues of the matrix A, lambda 1 to lambda n, are eigenvalues of U and the Koopman operator, and the associated eigenfunctions are given by the inner product of F, which is the functions that are in the representation, and Wj, which is the eigenvector of the transpose of A. So in that case, you can obviously obtain reduced representations by keeping only a few eigenfunctions, but you also have a full representation, that's given by, possibly faithful, that's given by this matrix. So the eigenfunctions of U themselves form an algebra. So if you have two eigenfunctions of U with associated eigenvalues lambda and beta, then the product is also an eigenfunction. That's proven very simply by the fact that composition distributes the product. And if one gets an efficient representation that is linear with some eigenfunctions of A, let's say A has a simple spectrum, that leads to many non-efficient representations that can be obtained by just adding products of eigenfunctions into the set of representation functions. So so you can create many eigenfunctions from these essential or principal ones. Let's talk a little bit about eigenfunctions and geometry now in the context of level sets. So if one finds a Koopman eigenfunction of a continuous time system, and then the level sets of that eigenfunction are elements of the invariant partition. So the partition into level sets of the eigenfunction is invariant in the sense that each element, each set inside the partition gets mapped into another set of the partition. So there are really two types of partition that are of interest. For measure preserving systems, recurrent invariant partitions are interesting. So these are invariant partitions such for that any set A, there is no time tau, such that the distance between A and its image under the flow is bigger than equal than epsilon bigger than 0 for some epsilon, and all t bigger than tau bigger than 0. And then an invariant partition that is not recurrent, we are going to call non-recurrent. So the recurrence really means that an initial set A always kind of comes close in this Hausdorff distance under the flow of the map, always kind of recurs. And the non-recurrence is the complement of that. Some examples of fixed invariant partitions. Here are some trajectories of a kick pendulum. Are, for example, ergodic partitions or fixed partitions. So the ones that all the points inside one level set stay on it, right? So these are fixed partitions. The other type of partition that you can have is when you have an element of the partition and all the points on that element jump into another element of the partition. For example, isochrones that I'm showing here for the van der Pol oscillator and isostables are such partitions. In this case, isochrones are actually recurrent because this is going to go to that, and so on until it returns back. But isostables are going to asymptote to the limit cycle. And so starting from some isostable here, we're going to meet other elements of the partition, but never come close back to the original. After a certain time t, you're not going to come back to the original element of the partition. So so now we come to the question of nonlinear representations. Everything we discussed so far, or rather, the examples that we discussed so far had the partitions have been induced by eigenfunctions. The representations are, the examples that we had are eigenmatrices and therefore linear, and therefore we can use eigenfunctions and perhaps generalize eigenfunctions to find linear representations, linear finite dimensional representations. And that's all fine as long as the Koopman operator has a point spectrum and has eigenfunctions. But if it doesn't, then it's an interesting question to ask whether there is a possibility of finding a set of observables such that it's in some sense closed. So if I know the value of that set of observables, then I'm going to know the value of that set of observables for any time in the future. So the space of observables that are constant on joint level sets of F turns out to be a linear subspace of O. So we pick a set of observables O F, and then we construct the space of observables that are constant on joint level sets of F. And that is a linear subspace. If you take two observables in that space, then they add to another observable in that space because that observable must be constant on the joint level sets of F, functions in F. So we're going to call a subspace of O to be generated by a finite set of functions if it is the subspace OF containing all observables G that are functions of F. And so a finite dimensional invariant subspace of U spanned by observables in a linear representation of dimension n is a span of generalized eigenfunctions. But a finite or infinite dimensional invariant subspace of U, OF, is the invariant subspace generated by F. So the question is, in the case when one has the infinite dimensional invariant subspace, is there a subset, or is there a closure for that set of functions F? So what that means is that the action of U on F would be given by some finite dimensional map, capital F, acting on F, and this map we call an eigenmap. Now, this problem can be solved, possibly, for example, using neural nets, if the observables themselves, so the functions in this F here, are represented by some neural network that has parameters theta, and then the map is represented by another neural network that has parameters psi, and then minimize over theta and psi the difference between the forward mapping so the forward value of the observables and the mapping on the value of the observable on the point mj, so at the current state. So there's one possible way of solving for capital F and the set of observables at the same time, but that's the key point. In the classical eigenproblem, one assumes the structure of the mapping F by saying, oh, it's linear. I'm going to find a single function and a scalar value such that this capital F becomes just lambda times some phi, single function. Here, one has to find, so in that case, one has to find lambda and phi. In this case, one has to find a whole set of functions, F, and the mapping itself. So it's a more complicated, certainly much more complicated numerical problem to solve. Now, let's go back to that expansion formula. I mentioned that if you have some x dot is equal to f of x, this could possibly be an evolution in an infinite dimensional space, really. Then in L2, in the Hilbert space of mu, we have this coherent part of the illusion and the continuous part of the illusion, as I have indicated through this discussion of representations. If one has just the eigenfunctions and no continuous spectrum part, then linear representations are possible. If one has no eigenfunctions, then the only hope one can have is a nonlinear representation, and that's as the consequence of the possibility of having a continuous spectrum. Some seemingly very simple systems possess only nonlinear representations. For example, non-harmonic oscillators in action angle form possess only nonlinear representations, but they're in classical dynamical systems called integrable systems. You can actually solve for their dynamics, but from this perspective, their dynamics is fundamentally nonlinear. Now, of course, chaotic systems have continuous spectrum, and so therefore can only be represented by finite-dimensional nonlinear representations. Now let's talk a little bit about numerical analysis. There are really two types of numerical analysis that we pursue in the context of Koopman operator theory. One is associated with averages, time averages, or weighted time averages along trajectories, and that goes under the name of generalized Laplace analysis. And the other one is, and in that case, we don't represent the Koopman operator itself. We try to find spectral objects like eigenfunctions. We try to find them directly without ever exhibiting the operator, directly from data. The other one is what goes under the broad name of dynamic mode decomposition, where we try to represent the operator using a finite dimensional matrix. And in that case, as you will see, the elements of the matrix are also obtained using time averages along trajectories. So that's also available from data directly, but these are two spiritually very different approaches. One of them has to do with the idea, let's not exhibit the operator, just find the eigenfunctions if there are any, or as I'm going to show you, parts of continuous spectrum as well. The other one says, let's represent the operator and then possibly find the eigenfunctions. So the generalized Laplace analysis, as this theorem says, applies when, for example, you have L0 to Lk eigenvalues of the Koopman operator, and they're ordered somehow by magnitude. And then you form these averages along trajectories. I'll show you some examples in a second of what these are, but in spirit, they're always weighted by the power of the associated eigenvalues. And then they contain the ith evaluation of the observable along the trajectory. Now we subtract some parts here, and these are the parts that have to do with already found eigenfunctions that correspond to the eigenvalues that are larger. So in the stable case, the slower decaying eigenvalues. So that might seem a little bit complex, but in fact, here is a simple example. If you have a time evolution, you have some flow phi t, then f is your observable. You multiply with e to the minus I omega t. Omega is real. These are what we call the Fourier averages. If omega is 0, in fact, this is just a simple time average starting from point x. And that way you can obtain invariant sets. The resulting function of initial condition is in fact an invariant function, and its level sets are invariant sets. And here I'm showing an old result from a paper with Zoran Lidnaj a long time ago. These are invariant sets of the kicked pendulum, quite an interesting image. If omega is different from 0, for example, for the van der Pol oscillator here is its limit cycle. Here is x1 and x2, here is its limit cycle. If we put omega exactly the frequency of rotation on the limit cycle, we're going to get those isochrones. So the level sets of the associated eigenfunction are isochrones. Now, if we put, instead of I omega, lambda here, and lambda is exactly the decay exponent, the flow k exponent, then we get the isostables. And these are all examples of this general formula that was generalized Laplace analysis that, as I said, comprises evolution along or time averaging along trajectories. The other approach is to say that, as I said at the beginning, the Koopman operator under certain technical conditions can be represented as an infinite dimensional matrix. So let's just choose a finite section of that matrix by cutting it off at n by size n by n. And that's clearly what is called the Galerkin projection or the compression in numerical analysis. So you first project to the finite space of observables you choose, you evolve by the Koopman operator, and then you project. That might take you out of that projected space, and then you project back. Interestingly, these values, the approximate values, can again be obtained as time averages. You know, a number of papers. It's standard now to write this as in terms of the Moore-Penrose inverse, but in fact, these elements can be written down in terms of f, the observables, then these g's that correspond to the dual basis to the set of observables, and taking their time averages along trajectories. So again, the time averages show up, and you can get the elements of this matrix directly from data. Now another aspect of this is that, that actually takes you to infinite dimensional invariant subspaces naturally and natively, is taking time delays. I've talked about the Takens theorem and time delays. Here we start with a single observable f, and then we time delay n times. And that forms a subspace again. And if we take that n to infinity, we get a cyclic subspace that is actually invariant. If we compose any function in it with t, we're going to get another function in it. So that's a way of getting invariant subspaces. The associated representation here can be obtained in terms of the companion matrix. And if the Krylov sequence itself satisfies that the nth iterate can be represented very nearly by the linear combination of previous iterates, then an eigenfunction of the finite section of this is in the epsilon pseudospectrum of the operator. So that's giving us ability to go from finite section to eigenfunctions through a very precise requirement on the Krylov subsequence. And of course, one would say, well, if the system has continuous spectrum, then somehow that shouldn't work. And indeed, so the precise requirement that you need to put in instead of the previous one, that is very general, this one that says that the Krylov sequence must satisfy this, is in fact that the underlying system has a pure point spectrum. And then we can generate a Krylov sequence and get that eigenfunction. This is the approximate eigenfunction, approximated very well for any epsilon bigger than 0. So we can approximate it arbitrarily precisely. So again, the point spectrum enables us to find eigenfunctions, enables us to find finite dimensional subspaces. A counterexample where we have continuous, or not a counterexample, but an example where we have continuous spectrum, we can't really do that, is this map on a circle S1 given by Z prime is Z squared. That's just, of course, in terms of real variables, X prime is 2X mod 1. If you construct the action of the Koopman operator on the harmonic functions, e to the ij theta, then you see that e to the ij theta gets mapped into e to the ij2 theta. That's just the square of the underlying observable. And and that never closes. You act on that function again, is going to have a 4 here, 8, and so on, so forth. So the matrix representation is something like this. The only eigenvalues that the system has, any finite section has, is are 0 eigenvalues. And on the other hand, this is a measure preserving system, and so its spectrum is on a unit circle. In fact, it's the whole unit circle. And so the finite section method actually will certainly fail here, although it's going to produce some spurious eigenvalues at 0. All right. And the last thing I'm going to say about the computation is, how about when we don't have a linear representation? So we don't have eigenfunction, can something still be done? Using the concepts in generalized Laplace analysis, indeed, this is a figure from work with Milan Korda and Mihai Putinar. And so in this case, we were looking for projections on a finite subset of the spectrum for the Lorentz attractor, which is chaotic, probably mixing, and therefore doesn't have any eigenfunctions that we could use for a finite dimensional linear representation. But this projection of f can be obtained in a similar way as those averages. You see, this is the kth iterate of the function, and this is some coefficient that depends on k and n. So k is the index and n is the length of the sequence. And then taking this limit to infinity, we obtain the projection on the appropriate subspace of the Koopman operator. And this in principle can be an infinite dimensional subspace, as is appropriate for continuous spectrum. Now, what are these coefficients alphas? Well, they consist of basically harmonic averages that I've shown you before, evaluated at endpoints. And then also this term beta that contains in it a coefficient that depends, it's 1 over k. So previously you had e to the I omega, but here you have 1 over k. So these are more like Hilbert averages, if you take a look at, or Hilbert transforms, if you take a look at ergodic theory literature. What you get is really interesting. The spectrum of the Lorentz attractor has a peak at a certain frequency. And if you take a small interval around that frequency and project on that, you get something that's almost like a sinusoidal function on the attractor. And the prediction that you can do, if you just want to predict the values of this function whose values are represented pictorially here, a real part and imaginary part, the prediction horizon for that is much longer than the prediction horizon for example, a x1 or xyz, x1, x2, x3 in this case. So there are these parts of, or there are these special observables that present you with almost linear behavior on finite time scales. And so we know that Lorentz has obviously a nonlinear representation. That's where we came from, the 3 ordinary differential equations. But this shows that there are observables for which Lorentz dynamics is almost linear on finite time scales. All right, and here are my conclusions. I've set up the learning of dynamical systems using Koopman operator framework within the theory of what I call the representations of dynamical systems. For linear representations, we find generalized eigenfunctions, and then we project observables on those to get Koopman modes or models or whatever we need in that context. For nonlinear representations, we need to search for infinite dimensional invariant subspaces. And these are, they can be reducible to linear provided that the system has point spectrum. But in general, if the system has continuous spectrum, then they're not reducible to linear, finite dimensional linear representations. I've discussed the numerical analysis. Using general Laplace analysis, we need to actually compute the eigenvalue somehow, and then get eigenfunctions and modes, and then we would get a linear representation out of that. Now we can also get a hold of continuous spectrum, which of course requires nonlinear representations using these Hilbert averages. And then numerical analysis using finite section, there are precise conditions on which it works. There are precise conditions on which it converges, but a continuous spectrum is very tricky to obtain using those. So here are some papers that I've drawn from. The most was drawn from this paper here that I mentioned at the beginning. There is another one that is an archive, and then a paper with Korda and Putinar that was published in Applied Computational Harmonic Analysis. And that's it for my talk. Thank you very much for your attention.